All right, this is chapter 10, electromagnetic induction. So in chapter 8, we've seen the effect of the magnetic field and the magnetic force. In chapter 9, we've seen the source of this magnetic field. It is the current. So the current in the wire will create a magnetic field around itself. Now in the 1800, physicists were asking the question, is the reverse possible? Is it possible to create a current from a magnetic field? And what they discovered is a changing magnetic field in time will induce a current inside a closed loop. Now, in order to understand this concept, we need to define the magnetic flux, which is very similar to the electric force. Okay, so let's start. Now, keep in mind, everything we're going to see in this video is related to a closed loop, the magnetic flux inside a closed loop. That's really important. All right, so the definition of the magnetic flux, we use a symbol phi with the uppercase letter B over here. It is equal to the dot product between the magnetic field vector multiplied by the area vector, which is also equal to the magnitude of the magnetic field multiplied by the magnitude of the area vector multiplied by cosine of the angle. All right, so that's it for the flux. Let's see at how we can define this induced current from a changing magnetic field. And we're not going to define directly the current, but we can find the electromotive force in volt. So the electromotive force, we use the letter E, so I modified E like this, is equal to the minus the derivative with respect to time of the magnetic flux. All right, so from this, we can calculate the voltage difference around a closed loop. And if we know, let's say, the resistance of that closed loop, we can calculate the current. All right, now, if we have multiple closed loop stacked on top of one another, we can create a bigger electromotive force. And we have to take this into consideration. So if we have n loop, this formula we simply multiply by the number of loops. So we add uppercase N for our number of loop. Now let's look at all of these formula together. This is our magnetic flux. And the change is the electromotive force induced in volt depend on the change of the magnetic flux in time. If we look back at the formula of the magnetic flux, there are three variables. There's the magnetic field, there's the area, and there's the angle between the two. If you change any of these with respect to time, you will induce an electromotive force. Now in the real world, it's possible to change many of these at the same time. In this course, what we're going to do at the beginning, we're going to see what is the effect of changing the magnetic field on the electromotive force. Then we're going to see what is the effect of changing the area on the electromotive force. And finally, we're going to consider the case of what happened when we are changing the angle with respect to time on the electromotive force. We will see also that this last one is the basic principle of generator in any power plant, really. Like in Quebec, we have the hydropower, so we have magnetic, big magnet. We spin the magnet and there's a change in electric flux and we use it to induce a current and create all the electricity that we consume in our day-to-day life. All right, so in the next video, what we are going to cover is, okay, we know what creates this electromotive force, and we will need to figure out in which direction it will point, in which direction the electromotive force will point. And what we will see is that it is a consequence of Newton's third law. If we increase the magnetic field in direction, you increase the force on the charge, and this increase in force is resisted, and it will create a reverse electromotive force. All right, so in the next video, we are going to tackle Lenz's law, which is a trick to figure out in which direction the current will be induced, basically. All right, so see you in the next video.